Hello, my name is Christoph Feichtenhofer and I'm a research scientist at Facebook AI Research. And in this tutorial, I will discuss some basic and recent architectures for efficient video recognition. Here is a course outline of the talk. I will first talk about video representation learning, then introduce a lightweight modeling architecture and a method to accelerate training. Finally, I will present recent work on audiovisual learning and an outlook. All the code for these methods will be available at this GitHub link, Facebook Research/SlowFast, which is our PyTorch codebase for video understanding. For the first part on representation learning, I will talk about a model called SlowFast. For this, I will briefly introduce the task, which is human action classification and detection. Here the goal is to detect all atomic actions that people are performing in the scene. So this image is a sample from the EVA dataset with the ground truth actions shown at the bottom. For example, the person on the left is standing, carries an object, talks to a person, and also watches a person while doing so. Note that many of these actions are not able to be recognized from a single image. For example, if the person on the left is talking and the person on the right would sit down. This makes this task particularly interesting, as only a method using 3D spatiotemporal information can solve this problem. On the top of the people, you can see the predictions of our SlowFast model that will be described in this talk, along with several other components for state-of-the-art video understanding. So video classification is typically done with 3D convolutional networks. The basic idea of these models is to have a spatiotemporal filter bank, as the 4 filters, for example, shown on the top left here. And then to spatiotemporally convolve an input video clip. And this is similar to image classification, only that now you have a third temporal dimension. The output of each convolution stage are 4D tensors of shape t times h times w times c for the time, height, width, and channel dimensions. A 3D convnet simply consists of several layers of 3D convolution, and after each filtering stage, the receptive field of the filters on the input increases, as shown by the growth of these filters when convolving them over the input clip. So the network reduces the spatiotemporal resolution of the output tensors from the input to the output, while it increases the number of channels C of the filters, or the number of filters, until the prediction is formed at the output. So at the output of the network, the prediction is formed, and the intermediate filters capture local information in X, Y, Z with growing receptive field sizes. SlowFast is loosely inspired by neuroscience. Please have a look at the following video from an experiment around 50 years ago. Isn't it amazing what our brain is able to do with just motion information? Just a few dots that move in a certain way can give us a very good hint about which action a person is performing. So for the human brain, motion is such a rich source of information. So what do we know about the brain? We know that there are 2 pathways. The ventral or WAT pathway is responsible for object or face recognition and builds upon parvo cells, which are the majority of the cells in the retina, the P cells. These cells have a slow conduction rate, which means they can only slowly propagate information and semantic information, color and semantic information. The dorsal or VER pathway, on the other hand, is responsible for motion recognition. And it builds upon magnal cells, M cells, and these cells amount to less than just 20% of the cells in the retina and can only process coarse grayscale information. However, they operate at a fast refreshing rate. Notably, we also see lateral connections between the 2 pathways. So the basic idea of the SlowFast network architecture is to have a slow pathway that captures semantic information by operating at low frame rate, and a fast pathway that captures motion information at a higher frame rate. So the slow pathway here is a spatiotemporal residual network, similar like the convolutional network shown before, that is applied to low frame rate video and therefore has a lower temporal resolution T. In contrast, the fast pathway is responsible for capturing rapid motion by operating at alpha times higher frame rate. Despite its higher temporal resolution and frame rate, this pathway is very lightweight, with only just 20% of the overall computational cost, by having better times less feature channels. In analogy to the Magno-Parvo ratio, two pathways have fused bilateral connections between them. So for example, to recognize the hand clapping action of the person on the right here, high frame rate is really needed to get this action recognized. Next, so the SlowFast network itself is represented now in detail in this table. This table shows an example instantiation of a ResNet 50 version. The dimensions of the kernels are denoted by T times S squared and C, where T is the temporal resolution, S is the spatial resolution squared, because usually we have two spatial dimensions, and C is the number of channels. The strides are shown as temporal and spatial strides squared, and the residual blocks are shown in brackets, and none that generate temporal convolutions are shown as underlined filters. So what we can observe here is that the input to the network is subsampled with a stride of 16 in the time dimension. So we take a small, a low temporal sample rate that subsamples the raw clip. And then this goes through a standard residual network, and the network has temporal convolutions only in the Res4 and Res5 stages. And the idea behind that is that that the late layers have a spatial receptive field that is large enough to capture possibly larger motion, and the larger motion because we have a stride of 16, which is a large change between the frames. Okay, so this is the slow pathway. The fast pathway is shown in the next column here. And the main difference to the slow pathway is really that we only subsample with a stride of 2 in time, which means we have high frame rate going through this pathway. And we also have beta times fewer channels. And here, alpha times more frames, which is, for example, 8 times more frames, but beta times fewer channels in these filters here, which means, for example, 8 times less filters in the fast pathway. Finally, what we show here is the output sizes of each stage. And you can see that the temporal dimension in the input is 64 frames, for example, times 2 to 4 squared spatial size. And then the slow and the fast pathway have 4 frames, and respectively the fast pathway is 32 frames. And this is held constant throughout the network, which means there is no temporal pooling that is applied throughout the network. And the spatial resolution is downsampled up to the last layer, where it's global average pooled and classified into number of classes. So the next slide, we show some ablations where we compare the slow pathway shown in blue dots against the SlowFast variant to their various models of different computational complexity for various slow models that you can see here. On the vertical axis, we can see the recognition accuracy. And on the horizontal axis, we see the model capacity and floating point operations, so the cost of the models. So we observe by the green arrows now that adding the fast pathway can bring significant accuracy gain, shown by these arrows, of up to 3.4% top 1 accuracy, at a relatively low increase of complexity, since the fast pathway is very lightweight. The model can perform state-of-the-art on multiple data sets for action classification and detection. So for action detection, we here look at the AVA data set and some class level performance. So adding the fast pathway here of the SlowFast model over the slow model shows that especially for high dynamic action classes such as dancing, running, fighting, or hand clapping, We can observe a substantial boost in mean average precision here. Now, our detector is similar to a faster RCNN applied to video to get these detections shown at the output side here. Detected boxes we show in green and ground truth boxes in red. Our action detections are shown on top of the people with the confidence scores, while the ground truth labels are on the bottom. The video illustrates the difficulty of this task, as multiple actions have to be localized in both space and time. In comparison to previous work, SlowFast has achieved a significant gain in detection accuracy. We also participated in the ActivityNet Challenge last year, where we saw a gain of 13 MAP over the winning approach from the previous year. Moreover, here the top 3 ranked teams all used SlowFast Networks as backbone, which underlines that the method is general and well received by the community. So this concludes the part on the SlowFast networks, and now I move on to discuss the difference of training duration for a ResNet 50 model on ImageNet versus a 3D ResNet 50 version of that model on Kinetics. While on ImageNet training time is around 1 day on a single GPU, on Kinetics we have training duration that is around 14 days. So this has 2 main reasons. The first, models are more expensive, and second, training is less efficient. So we will now have a look at 2 approaches that can increase this efficiency. So first I will talk about how to increase the efficiency on the modeling side by talking about X3D. So for 2D tasks such as image or object recognition, it is common to apply layers of 2D filters to input images, which results in feature tensors of size h times w times c. For video recognition, an intuitive way is to convolve an input video clip with 3D spatiotemporal filters. This is typically done by extending an image-based network by a 3rd dimension. Basically, nearly all video classification backbones are temporal extensions of ImageNet design. Therefore, the h times w times c dimensions are fixed based on the ImageNet design. Our claim in this work is that direct temporal extension is suboptimal for efficient video recognition. Our idea is called X3D, which is an architecture that is expanded from a tiny image model across multiple axes to achieve good computational accuracy trade-off. The tiny model is shown on the right and called X2D. Here you can see that it has tiny resolution at the input channel and depth, and different colorized gamma variables in the table are factors that are used to expand this model. The candidate axes are frame rate, temporal duration for all the activations and the input, spatial resolution for the input and all activations, network depth, the width of the network, and also the width of the bottleneck in the residual block, which is a channel-wise 3x3x3 convolution. So importantly, this spatiotemporal convolution in the center of the residual block is channel-wise, or also sometimes called depth-wise separable, which are commonly used in mobile networks and have very favorable floating point and parameter trade-offs. To generate X3D, which is expanded across multiple axes for good computation accuracy trade-off, the idea is to progressively expand this tiny base 2D image architecture into spatiotemporal one by expanding these multiple possible axes. And we have 6 expansion operations that expand each across one of these axes. And the idea of the expansion is to progressively increase the computation by, for example, 2x by expanding one axis at a time, then train and validate the resultant architecture, and select the axis that achieves best computation accuracy trade-off. The process is repeated until the architecture reaches a desired computational budget. Here we compare one X3D model from this expansion process shown on the right side to the meta-architecture of the previously introduced SlowFast model on the left side. The two models achieve roughly the same recognition performance on a kinetics action classification task. Despite several other differences that we ignore for now, like the channel-wise convolution, we observe that the number of feature channels are quite different. So X3D on the right side has a low channel width, which is only slightly higher than the very lightweight fast pathway shown on the left here. And it's significantly lower than the number of channels in the slow pathway shown on the very left. And when comparing the output dimensions of each stage, we see that X3D has a temporal resolution that is in between the slow and fast pathway with 16 frames, whereas the slow pathway is 4 frames and the fast pathway is 32 frames. So overall, this model seems to find a good trade-off between the slow and fast pathways in SlowFast. In the experiments, the expansion starts with X3D, the tiny image model with a single frame, and expands it first across the bottleneck width of the model, then the frame rate, the spatial resolution, the depth, the network, and finally also the global width of all layers. The output of our expansion are a sequence of models from extra small to extra large capacity. So we exponentially increase the model complexity in each expansion step by doubling it. The plot shows vertically the classification accuracy and horizontally the model capacity and floating point operations. Only the last step increases the global width of the model, which shows that the channel dimension can be very small for video recognition, which was also key for the fast pathway in SlowFast networks. Here we compare to the previous work. The graph shows SlowFast models in green, channel-separated networks in pink, and temporal shift module in gray. The number of clips used for testing is shown in the individual points. Comparing to these works, we see that the floating point operations can be dramatically reduced with X3D, with reductions of up to 10x for large and small models. Concretely comparing to the state-of-the-art CSN numbers, X3D provides a 5x reduction in floating point operations and parameters. Here it's to note that X3D has the advantage of channel-wise convolution, which makes a direct flop and parameter comparison to SlowFast not fair, because it does not use channel-wise convolution, which has inherently much lower floating pointing operations and parameters. The paper has further experiments on charades and AVA where the same observations hold. Next, I talk about another method to accelerate training of video. Since in video modeling we're dealing with large feature tensors, the batch size we are using are typically small. However, GPUs inherently benefit from large batch sizes to accelerate training with parallelization. The method is called Multigrid, and it allows us to decrease the training duration for training a video model such as SlowFast networks, shown in this graph, by 4.5x, which provides a slightly higher accuracy as well, of 76.4% versus the SlowFast baseline that has 75.6%. To increase the training speed would be to use small input resolution and large batch sizes, as shown here on the left. But this will result in lower accuracy compared to a large resolution input with small batch size, shown on the right. In multigrid training, we increase the batch size in a cyclic manner by reducing the spatiotemporal input resolution. Our long cycles span several training iterations of lower input resolution. First, that start with a 4 times lower resolution but an 8 times higher batch size, and then progressively increase the input resolution during training. So overall, this would allow us the concrete schedule of 4 different steps in the cycles stages to use 3.75 more training examples during training compared to standard training. We also used the so-called short cycles, which change the spatial resolution and batch size in each subsequent training iteration, as you can see here. So this does not change the temporal resolution. So if we use both the long and the short cycles combined, we end up with a multigrid training paradigm like this, shown here. So overall, we have 4 cases. First, the baseline method that uses a fixed batch size during training. Second, the long cycles, which increase resolution over training, both spatially and temporally. Third, the short cycles, which quickly change the resolution each training iteration for a spatial input size. And fourth, the combination of the two, which is our multigrid schedule, combining long and short cycles. In the paper, we applied these 4 variants. This figure shows the accuracy and training time for a fixed batch size. So here you can see the accuracy for training with different number of epochs. 1x is the default training duration and schedule, and 0.5 means, for example, on the left of the plot, that we only use 1/4 of the overall training epochs. So we can see that just using shorter training duration and schedule drops accuracy significantly, and training longer than 1x does not increase accuracy anymore. So one ablation we will be doing and can do is using a smaller spatiotemporal scale for training. And this, of course, decreases the training duration. It allows quicker training, but it also drops accuracy sharply. Another ablation we're doing is using the short cycles now, which changes the spatial resolution and batch size in each iteration. And we can see that this provides a 3x speed up compared to the default constant input resolution in blue. Next, the long cycle, which also changes the temporal resolution and not just the spatial one over the training duration, provides an even larger improvement of 4x in the training duration compared to the baseline. Finally, the combination of the two ends up at 4.5x speed up that combines the long and the short cycles. In the paper, we explore this for various settings on 3 datasets, kinetics, charades, and something, with 3 models, SlowFast R50 and non-local, and various amount of GPUs used during training, from 1 to 128 of GPUs used. Now I would like to move on to multimodal learning with a recent work on audiovisual SlowFast networks. Since video naturally comes with both visual and audio information, it is intuitive to process these modalities jointly, which has typically not been done in previous work that treats the different modalities separately. So this motivated us for the following piece of work. The objective of this paper is to build an architecture for integrated audiovisual perception, going beyond previous work that performs late fusion. So we proposed audiovisual SlowFast networks that extend SlowFast networks with a faster audio pathway that is deeply connected and integrated with the visual counterparts by fusing at multiple layers. However, if one tries naive joint training of audio and visual modalities, it will not work and provide an even lower performance than a visual-only SlowFast model. This can be explained if we see the training dynamics shown on the top left curves. We see that audio alone in red here needs much fewer iterations to converge and then starts to overfit. To overcome this different learning dynamics, what we do in the paper is we use drop pathway that randomly drops the audio pathway during training, which enables us to train an audiovisual model jointly with hierarchical fusion connections between the modalities. In the paper, we show that audio can improve recognition performance across a variety of data sets and tasks. Sometimes it can provide larger improvement, and sometimes it provides slower improvement for different classes and data sets. Now, I would also like to show an example where we apply these audiovisual networks to self-supervised learning. And for this, we use audiovisual synchronization to encourage the network to produce features that are generalizable across modalities. So this is inspired by studies on the audiovisual mirror neurons in the cortex. Specifically, we add an auxiliary task to classify whether a pair of audio and visual frames are in sync or not. And in our experiments, we see that this audiovisual SlowFast architecture achieves state-of-the-art performance on multiple datasets for supervised classification and detection, but also on these self-supervised tasks. So here we pre-trained a model using an off-the-shelf pretext task and evaluate it against the state-of-the-art SSL methods. And we can see that we can achieve a good gain over the previous work in this space, just using this audiovisual SlowFast model for self-supervised learning. So finally, I would like to promote again our codebase called PySlowFast, where we implement all of these methods shown in the current talk. They will be available or are already available in this codebase right now. So please have a look if you would like to start in this domain to work on that. In conclusion, there are, in my point of view, three important aspects for moving forward in video recognition. So first, advancing and accelerating video modeling will need innovative models, such as X3D or SlowFast, presented in this talk, and also training strategies like Multigrid, for example. Second, the world is multimodal, and video captures this richness. I think our models should also hear and see. Maybe SlowFast is a first small step into this promising direction. And third, this goes without saying, the future will be unsupervised, and video is the medium that allows us to learn from spatiotemporal associations across modalities, predict the future from the past, and even perform higher level reasoning that take, for example, causality into account. Thank you, and I'm happy to answer questions during the Q&A.